Assalamu alaikum. I welcome you all to another lecture on power electronics. In the last lecture, we studied the DC to AC inverter. One basic type of an inverter, which is known as a square wave inverter, was actually studied. At the end of the lecture, we learned that there are certain drawbacks in a square wave inverter. One of the drawback is that the frequency component that is present in the system is of a very low frequency, and therefore bulky filters are required to get rid of the undesired harmonic content in the system. Another important issue in that square wave inverter was that there is no control on the output voltage. So in the today's lecture, we will move on with a modified form of a square wave inverter that addresses one of the problems that we discussed yesterday, and that problem is the elimination of harmonic content by introducing the zero periods in the system. Let us start with this today's topic. So let me draw the H bridge circuit here. This is the H bridge circuit. Here we have this load. This is S1, S2, S3 and S4. In the square wave inverter, we have utilized only two states that we turn on the switch S1 and S2 simultaneously to produce VDC. Then we use S3 and S4 combination to produce an output voltage VDC. In a quasi square wave inverter, to introduce zero periods in the square waveform, we require to use the third set as well, that is to turn on the switch S1 and S3 to get a 0 volt, or to get S4 and S2 to get the 0 volt. So together we have, in a quasi square wave inverter, we have three levels of output of output output voltage, right? So we require to have three different levels of the output voltage. What is the advantage of using these three levels of output voltage? Remember that in the last class we utilized the Fourier series to find out the harmonic content. So you can see here that the frequency component, if we draw it with respect to this fundamental component, then if this is the fundamental component, which is the first harmonic, if this is the first harmonic, then we have the third harmonic available, which has an amplitude something around one third of the fundamental component, so somewhere here. Then we have the fifth harmonic, then we have the seventh, ninth, 11th and so on and so forth. But the problem here is that if we want to get rid of these harmonic content, we require to have a two-stage solution that requires an additional filter here somewhere to get rid of these harmonics, and this filter is quite bulky. This is what we studied yesterday. Why it is bulky? Because for the square wave inverter, uh, or in for instance in the UPS, the current may be of 30 to 50 ampere, right? It may be in tens of amperes, and therefore that current has to carry and has to pass through this filter block, and therefore we require to have bulky and expensive filter networks to get rid of these harmonic contents. These harmonic content can be controlled up to some extent if we utilize this zero sequence in the system. By utilizing this zero sequence, we will get an output something like this one. So this is the V naught. This one. So here we have, this is pi, this is 2 pi, this is the zero period alpha, which is introduced at the start and at the end of each half cycle. So this is alpha, this is alpha, this is also alpha, and here we also have this alpha. Rest we have here is this minus VDC. Here we have the plus VDC, and you can see that by introducing these zero periods, this square waveform has altered and is now known as a quasi square waveform. So the definition of a quasi square waveform is quasi square waveform has a square wave with zero periods or zero instants, and this alpha is actually a controllable quantity. So with this alpha, a controllable quantity, it is possible to get rid of the selected harmonic from the harmonic spectrum, which is very helpful, because without using an additional filter network at the output of an inverter, this scheme provides us an ability to eliminate a certain group of harmonics or a certain harmonic. So for this quasi square waveform, the V naught or RMS value of V naught is given as V naught is equal to 1 over pi integral alpha to pi minus alpha V square DC d omega t, which is equal to VDC into 1 minus 2 alpha over pi, and the Fourier series for this quasi square waveform, the Fourier expression is given as again we have only the odd harmonics. This is Vn sine of n omega naught t, and luckily because of the half wave symmetry, this voltage Vn is equal to, let Vn is equal to 4 VDC over n pi into cosine n alpha. So this 4 VDC over n pi is same as that of a square wave inverter, square wave output. This cosine n alpha is the controllable factor, right? So because the switching logic or the switching scheme is in the control of the design engineer, therefore the specification of alpha can target any desired harmonic content. For instance, if this cos of alpha is equal to 0, if we make this term equal to 0, then that particular harmonic content will vanish from the output spectrum. So this controllable factor, if we make it equal to 0, that particular Vn becomes 0, right? So this cosine n alpha is a very important quantity in understanding the operation of a quasi square wave inverter. Cosine n alpha is the real hero in the whole system, where this alpha can vary from 0 to pi. You can vary this particular thing. Alpha is variable, and by shifting this from 0 to alpha, this Vn can also be varied, right? Also through this particular equation, let me write this particular equation. This is a very important equation. This equation provides us some important attributes here. The first thing is that this cosine and alpha can be varied from 0 to pi and therefore it can address any specific harmonic content in the output harmonic spectrum. The second important point that this provides us, that all the frequencies are alpha dependent. So it will impact the amplitude of all the other harmonics and as well as the fundamental component present in the system. So that using this particular one, the fundamental component V1 becomes equal to 4 VDC over pi into cosine of alpha. So this fundamental component is also depending on this alpha. So to target any particular harmonics, this cosine and alpha should be equal to 90 degree, because at 90 degree this cos function become equal to 0, thereby it will eliminate that particular harmonic content. This means that if this alpha is equal to 90 degree over n, right, where n is the harmonic component. For example, if we want to remove the third harmonic from the system, this alpha is equal to 30 degree, and for fifth harmonic this alpha is equal to 18 degree. So we can analyze a given inverter system, we can go through the Fourier series to visualize the harmonic spectrum, and thereby we can target the most dominant harmonic content in that system and eliminate it by specifying the value of alpha in the system. Before we move ahead, let us have a detour to the total harmonic distortion, because this is what we are actually heading towards. So let's have a quick detour here. Total harmonic distortion, or the THD, it is actually a method to mathematically quantify the quality of the output voltage of any given system. It is particularly used for the inverter output, because the aim is to produce a sinusoidal output by using these semiconductor devices. Here what we are getting, for the previous inverter we got a square wave, and here we have obtained a quasi square wave, both of which are not actually a sinusoidal waveform. So how can we actually quantify that, how close a given inverter is compared to an ideal sinusoidal waveform? So this total harmonic distortion provides us a method to quantify this particular expression mathematically. So for a square wave inverter, or for any inverter with 0 DC component, we have the total harmonic distortion is given as n is equal to 1 to infinity Vn RMS square divided by the fundamental component present in that given system, given RMS, right? This can also be written as V1 square RMS minus VRMS minus V1 square RMS divided by. Now these two components, these two equations are essentially the same. Important point here is that how can we ensure that a square wave inverter with zero DC component. This is accomplished by switching the diagonal pair of switches for equal duration of time. So this was also discussed yesterday, that the time for which we turn on the switch S1 and S2 should be equal to the time duration for which this switch S3 and S4 are turned on. This will ensure that the total area under this particular curve is equal to the area enclosed in this negative curve. So there will be a zero voltage shift or zero DC component in the system if we ensure this thing. So for that system, this THD is equal to V RMS square minus V1 RMS square over V1 into RMS, which is the fundamental component present in the system. Let us analyze the inverter example that we studied yesterday in terms of the THD, and thereafter we will apply the Quasi Square wave terminology to see the impact on the total harmonic distortion in a given system. Remember that this THD should be less than 5% according to the IEEE standards. Various other standards restrict it between 5 to 10% in order to have a clean the harmonic pollution in the national grid. So let us move back to this particular example. This is the example that we studied. Let us find out the THD of the voltage voltage spectrum for this particular example. So THD is equal to V square RMS minus V1 RMS square divided by V1 RMS, right? So what is V RMS here? V RMS is equal to VDC, that is equal to 100 volt. So V1 RMS is equal to V1 divided by under root 2, and that is equal to 112.5959 volt, right? So what is the VDC here? Let me recheck the VDC. VDC is equal to 125 volt. So let me alter this one. This is not 100 volt, this is 125. This is 125 volt. So the THD here is equal to 125 square minus 112.59 square divided by 112.59, and that turned out to be equal to 54.30 divided by 102.59, 0.48 or 48%. Now this 48% indicates that this particular inverter is not able to integrate itself or to supply the power to the grid because it is too much polluted. So how can we actually reduce this voltage harmonics? Let us design an inverter system using the Quasi Square wave. Now if you notice here that here we have the dominant harmonic content is this third harmonic that contributes to 53.05 volt and comes second after the fundamental component. Therefore, it is wise enough to get rid of the third harmonic from the system. So for this third harmonic, to getting rid of this third harmonic, let us do an example. Example 8.5. So we need to design an inverter that has an RL load, R equals to 10 ohm, L equals to 25 millihenry with fundamental frequency current amplitude of, we require to have the fundamental current amplitude equals to 9.27 ampere, and we also want to have a THD less than 10%, right? So we have a variable DC source through which we can actually vary the input voltage. So let us first of all compute the input voltage. Now fundamental current amplitude is given. Using this thing, let us first of all specify the voltage from this variable DC source. So we have this type of a system. This is an R plus L load, and we have specified that this I1 should be 9.27 ampere. What is the value of this VDC? So for this 9.27 ampere, the fundamental component has to be adjusted. So V1 is equal to I1 into Z1. What is this I1? Is 9.27, and what is this Z? Z is equal to R square plus omega L square, right? So for, let us say that the frequency, output frequency F is equal to 60 Hertz for the fundamental component. So this V1 comes out to be equal to 9.27 into 100 plus 2 pi 60 into 525 millihenry square, and that gives me 127 volt. So now that we have the voltage of the fundamental frequency available, we need to specify this VDC as well. Remember that using this particular expression, Vn is equal to 4 VDC n pi over into cos n alpha, and therefore if we know what is this V1, we can find out what is this VDC. So using this expression, VDC is equal to V1 pi divided by 4 cosine of alpha, and that is equal to 127 into pi divided by 4 into cosine of 30 degree. Why we have chosen this alpha equal to 30 degree? Because we have seen in the previous example that the third harmonic is the most dominant harmonic in the system. So if we reduce this third harmonic, we can bring this THD less than the desired value, which is 10%. So we have actually taken this alpha equal to 30 degree to target the third harmonic. So with this alpha equal to 30 degree, this VDC comes out to be equal to 116 volt. For the rest of the harmonic content, let us again create the table. So here we have this N, which is the harmonic content. Then we have F in Hertz. Then we have Vn into V. Then we have Zn in ohms, and then we have In in ampere. This is the first, third, fifth, 7th, 9th, 11th. So here we have 60, 180, then we have this 300, then 420, then we have 540, this 660. What is V and V? The fundamental component is equal to 127 volt. What about the third harmonic? Now the third harmonic is based on this particular expression. This one, Vn is equal to 4 BDC n pi into cos n alpha. So with this 3 and this 30, this become equal to cos 90. So this V third harmonic is equal to 0. Let me write this expression here. So this Vn is equal to 4 BDC over n pi into cosine n alpha. So using this particular harmonic, this becomes equal to 0. For the fifth harmonic we have 25.5, and then we have for the seventh harmonic we have 18.2, then 0, then it is 11.6. Similarly, we will find out what is this Zn here. Zn, again this Zn is equal to r square plus n omega naught L square omega L square, and using this we can find out what is the impedance for the nth harmonic. So for the fundamental component, this is equal to 13.7 ohm. Then for the third harmonic it is 30 ohm. For fifth it is 48.2. Then we have 66.7. Then we have 85.4. Then we have 104. And then by using this expression In is equal to Vn over Zn, we can find out what is the harmonic current for each component. So for the fundamental component it is equal to 9.27, which is exactly the same as given as desired in this particular example. Then we have 0, then we have 0.53, thereafter we have 0.27, then 0, then 0.11. So the THD of the load current can be calculated as the 0.53 divided by under root 2 square plus 0.27 divided by under root 2 whole square plus 0.11 divided by under root 2 whole square divided by the fundamental component, RMS value of the fundamental component. So that turns out to be equal to 0.066, or that is equal to 6.6%. So we have effectively reduced the current harmonics from the system by simply putting this alpha equal to 30 degree. Now let us see what is the impact if we instead of targeting this third harmonic, let us target this fifth harmonic. Now if this fifth harmonic is to be removed, right, I will alter it here, that for, let us say, for this one, for fifth harmonic, alpha should be equal to 18 degrees. If I put this equal to 18 degrees, then the first thing that we need to address is this VDC. If this alpha is made equal to 18 degree, then this VDC becomes equal to 104.87 volt, and thereafter we can actually address this particular thing with this alpha equal to 18 degree. This third harmonic content shall have a value equal to 26.16 volt. Here we have this 0, and then we have minus 11.211, then we have minus 14.10, and then minus 11.54, where this negative shows the phase shift. And also we have here, this is 13.7, this will be 29.9, this is 48.17, then we have 66.72, again because this will remain the same, it has nothing to do with this alpha, so these are exactly the same. However, we do have a difference in the current here, that is now 1.68.165, and then we have for the fifth harmonic content, this is equal to 0. Let me write it properly. So 0.87, then we have 0, then we have 0.168, thereafter we have 0.165, and then 0.11. So in this particular case, with alpha equals to 18 degrees, the THD of the load current becomes equal to 9.8%, which is less than the 10%. Both are provide us a value that is less than 10%. But here you see what is the advantage of having this third harmonic. With this third harmonic eliminated, you are not only eliminating this third harmonic, but you are also targeting the odd multiples of the third harmonic. For instance, this third is gone, this ninth is gone. So all the triplet harmonics are eliminated if the third harmonic is targeted in this particular system. So we have seen that effectively we can get rid of the harmonic content up to some extent by using this square wave inverter. But now let us have a question that how can we actually produce this type of an output waveform using this inverter. So let us move to the gating sequence for producing quasi output. So suppose that we have this inverter available. This is S1, this is S2, this is S3, this is S4, this is V0. So here we have an output voltage V0. So this is the output voltage, this is the output voltage, this is pi, this is 2 pi, this is alpha, this is also alpha. So what should be the sequence for turning on the switch S1, S2, S3 and S4? So S1 is turned on from alpha to pi plus alpha, because here we have the pi, so this alpha becomes equal to this alpha plus pi. For this S2 is turned on from alpha to from 0 to pi minus alpha, where this is pi. Similarly we have S3. S3 shall start from this particular point and we will turn this on till alpha plus pi. So as a result, let me also draw this S4 as well. Alpha S4 is turned on for this duration and for this much duration. So you can see here that for this particular duration, when this V0 is equal to 0, we have turned on this S2 and this S4 simultaneously, right? So S2 and S4 simultaneously produce 0 volt output here. So here we have this S1 and this is S4. Both are shorting the load, and hence we have the 0 volt appearing across this load. Thereafter we have this S1 turned on, S2 turned on. There is no S3 and S4 available here. So S1 and S2 provide you the plus VDC here. Then we have here alpha. This S1 is on. This S1 is on here, and also we have this S3 has to be on from here. S1 is on, S3 is on, and therefore we get 0 output here. After that we have S1 on, we still have S1 on and S3 on. So S1 and S3 are on, so we again have 0 output available here for this much duration as well. Just a minute, let me just write it here. This is somewhere here, this is here, and thereafter we have this S3 and S4 on to give you a minus VDC here. So this is the procedure of the gating sequence. But the question is, how can we simulate this thing? How can we specify those instants at which we want to turn on and off these switches? For that, I have developed two methods. The first one is, in the first method, these are my own methods, so maybe you may find it workable for most of the time because I have tested this one. So if the load is resistive, then S1 and S3 and S2 must be switched for 30 to 150 degree. You can specify it in the gating sequence in the PCM block, and this S3 and S4 are to be turned on from 210 degree to 330 degree. So we are actually producing a 30 degree alpha that targets the third harmonic here. But what if the load is R plus L load, or the inductive load? So for this inductive load, the expression that I have developed are quite simple. That is, to turn on this S1 is to be turned on from 30 degree to 210 degree. Thereby it will be turned on for complete 180 degrees. S2 is turned on from 0 to 150 degree, and then from 330 to 360 degree. So this is again equal to 180 degree. 30 degree coming from this side and 150 degree from the above expression. S3 is turned on from 150 to 330 degree, and that is equal to 180 degree. And this S4 is turned on from 0 to 30 degree and from 180 to 330 degree, again completing the total switching time equal to 180 degree. So every switch has to turn on for complete 180 degree. There will be overlaps between the switch S1 and S3 and S3, as well as switch S2 and S4, thereby introducing the zero periods in the output waveform. So in a generic waveform, so with respect to the alpha, this S1 is equal to alpha to 180 degree plus alpha. This S2 has to be on from 0 degree to 180 degree minus alpha, plus 360 degree minus alpha to 360 degree. So whatever is the amount of alpha, you can actually specify here. For this S3 we have 180 degree minus alpha to 360 degree minus alpha, and for S4 we have 0 to alpha, and, or let me use the plus sign here, this is plus, 180 degree plus alpha to 360 degree. So you can actually specify the value of alpha to get rid of any particular harmonic content. I have already done this simulation, which is available on my YouTube channel, and I will post the link below, as well as you can see the card upside. So you can click there and you can go through this PCM simulation to visualize that this harmonic suppression can be possible by using this Quasi Square wave inverter. But let us first of all analyze summarize this particular Quasi Square wave inverter. So we have the pros here. What is the pros? The number one is that the harmonic content is suppressed without using a filter network. This is the advantage. Rest, it suffers from all the cons of a square wave inverter. Number two, once alpha is specified, the output voltage is fixed, and thus it faces same issue as the square wave inverter. This is the first issue with that. The other disadvantage here is that the control factor cosine n alpha is not linear, right? So this is another issue with this particular type of an inverter. In the next class we will study the pulse width modulated inverters that address the voltage control as well as the frequency control, and it also has a linear control on the output voltage. So in the next lecture we will discuss these things. Till then, thank you very much. Take care. Allah Hafiz.